Good evening, everyone. Welcome to my channel Simplified Organic. Learn organic in a simple and easy way. Today's my topic is Geometrical Isomerism. Lecture 1. What are geometrical isomers? If I want to define geometrical isomer, what is the definition? The stereoisomers which differ in spatial arrangement of atoms or groups. The stereoisomers which differ in the spatial arrangement of atoms or groups across a double bond, or it can be a ring. So these type of isomers are called as geometrical isomers. The point to note here is to convert one geometrical isomer to other, we need to break a bond. We need to break and form some bonds. Without breaking a bond, we cannot convert one geometrical isomer to another. The best example is but-2-ene. For example, but-2-ene, CH3, CH double bond, CH3. This we can represent in two different ways. First one, where both the methyl groups are on the same side of the double bond, which is called as cis form. And the another one is where both the methyl groups are in the opposite side of the double bond, called as trans form. This is the best example we can define, which can easily explain the geometrical isomer. So in this case, the methyl groups are differing in the spatial arrangement across the double bond. These are called as geometrical isomers. The stereoisomers which differ in the spatial arrangement of atoms across the double bond or across the ring are called as geometrical isomers. Now, let us go for the conditions. Very important. Conditions to identify whether a compound can show geometrical isomerism or not. What are the conditions to identify whether a compound can show geometrical isomers or not? The first condition is restricted rotation. What do you mean by restricted rotation? Where the rotation of the bond is restricted. Like for example, if I take any sigma bond, the sigma bond can easily rotate. Single bond. If I take a single sigma bond, it can easily rotate. But when you take any double bond, any unsaturation, you cannot rotate this sigma bond. This carbon-carbon bond cannot be rotated. Carbon-carbon bond cannot be rotated. What is the reason? Very simple. If we rotate this sigma bond, the pi bond which is formed due to the overlapping of the p orbitals, the pi bond which is formed, that pi bond will break. It will break. So we cannot rotate a double bond, carbon double bond. We cannot rotate. There is a restricted rotation in that. Single bond can easily rotate it, no problem, but double bond we cannot rotate. In the same way, triple bond also we cannot rotate. Triple bond also have the same condition. We cannot rotate carbon-carbon bond. Like another example, any cyclic compound, okay, up to 6-membered ring, up to, I can say, sometimes I can say 7-membered ring. So I'll discuss this later. So like cyclic compounds, like if I take cyclopropane, take any 2 carbons. If I take 1, 2, 3, I cannot rotate 2 and 3 bond. If you please check here, I cannot rotate 2 and 3 bond. It's not possible. Why? Because carbon 1 is joining carbon 2 and 3. So it is not possible to rotate carbon 2, carbon 3 single bond. In the same way, I cannot rotate 1, 2 carbon single bond. I cannot rotate 1, 3 carbon single bond. So overall, I cannot rotate any of the sigma bond here. So select any 2 carbons. Like for example, if I select these 2 carbons, 2 and 3, I cannot rotate 2 and 3 bond. So there is a restricted rotation in this. There is a restricted rotation. In the same way, if I take cyclobutane, select any 2 carbons. If I select these 2 carbons, I cannot rotate this single bond here, not possible. So there is a restricted rotation. If you rotate that sigma bond, the ring will break, not possible. In the same way, cyclopentane or cyclohexane, etc. So any cyclic ring up to 6-membered or 7-membered, we cannot rotate. So there is a restricted rotation. So this is the first condition to show geometrical isomerism. That is, there should be a restricted rotation. Like for example, N double bond and yes, there is a restricted rotation. N triple bond N, yes, there is a restricted rotation. For example, C double bond O, there is a restricted rotation. O double bond O, C double bond N, etc. In these type, there is a restricted rotation. So first condition is satisfied. Now coming to the second condition, that is different atoms or groups should be bonded to stereocenter atom. Now, I'll explain you this. What do you mean by stereocenter and all? See, wherever you are studying geometrical isomerism, wherever we can study stereoisomerism. What do you mean by stereo? Many like geometrical isomerism or optical isomerism. Wherever we can study stereoisomerism, that center is called as stereocenter. That center is called as stereocenter. For example, I have C double bond C, and this C double bond C is a stereocenter. If this is stereocenter, if it is stereocenter, these atoms are called as stereo atoms, stereo center atoms. I hope you got this. Wherever you are studying geometrical isomerism or optical isomerism, that center is called as stereocenter, and the atoms are called as stereocenter atoms. Now, what is the condition number 2? Condition number 2 says they should be different atoms or groups bonded to stereocenter atom. Means on this carbon there should be 2 different groups, and on this carbon there should be 2 different groups. Then only geometrical isomerism is possible. For example, I have C double bond C, and I have branches like A, B, B. The point is, can this show geometrical isomerism? So the answer is no, it cannot show. It cannot show geometrical isomerism. What is the reason? Because it have both same groups. These are same groups. Here also there are same groups. So therefore, this cannot show geometrical isomerism. To show geometrical isomerism, these groups should be different, or these atoms should be different. Then only it can show geometrical isomerism. Like for example, once again, I'll repeat the same example, that is but-2-ene. What is the structure? CH3, CH double bond, CH, CH3, but-2-ene. Okay. Now in this case, first condition, yes. First, I'll just write this. I'll write it in open structure form. First condition, yes, satisfied. There is a restricted rotation. Yes, there is a restricted rotation. And what is second condition? Different groups. See, here you have a methyl group and you have a hydrogen. Here also you have a methyl group, you have hydrogen here. So if you check this stereocenter carbon, okay, one second. If you check this stereocenter carbon, it have a methyl and a hydrogen. Yes, both are different. And here also this carbon have methyl and hydrogen. So these two are also different. So therefore, this can show geometrical isomerism. So if it can show, how many ways we can write? Those all we'll discuss later. Now today's my topic is whether it will show or not. Whether a compound given to you can show geometrical isomerism or not. That is the point I'm going to discuss today. For example, like I have 1, 2. For example, I have 1, 2 dimethyl cyclopropane. For example, I have 1, 2 dimethyl cyclopropane. So see, this is a cyclopropane, and here one methyl, here one methyl, 1, 2. So if I write stereocenter here, see, this is a stereocenter. Okay. Now if I write this structure here, C, and it is bonded with third carbon. Now this carbon have a methyl group and a hydrogen, and this carbon have a methyl group and a hydrogen. Now please check this carbons. This carbon have a methyl and a hydrogen. This carbon have a methyl and a hydrogen. So therefore, this can show geometrical isomerism. So this compound can show geometrical isomerism. In the same way, in the same way. For example, I have cyclobutane 1, 2, 1, 2 dimethyl cyclobutane, right? So now please check this stereocenter. Check this stereocenter. Now if I write this compound properly, carbon, 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 and here this carbon have a methyl group and a hydrogen. This carbon have a methyl group and a hydrogen. So now check this stereocenter atoms. This carbon have two different groups. This carbon have two different groups. Therefore, this can show geometrical isomerism. Can show geometrical isomerism. So likewise, I can discuss many more examples. Like for example, I have N double bond and this is called as azo type. Okay, this is called as inimine. Okay, so now when you check this N double bond N can act as a stereocenter. This N double bond N can act as a stereocenter. And this nitrogen have a hydrogen and a lone pair. And this nitrogen have a hydrogen and a lone pair. So I want to add one point. You can consider lone pair as a group. You can consider lone pair as a group. Can consider lone pair as a group. Now this nitrogen have two different groups. These two are different. And this nitrogen also have two different. These are different. So therefore, this compound can also show geometrical isomerism. This can also show geometrical isomerism. Like few more examples, if I take, you might have studied about this. This is called as oxime. This compound is called as oxime. Now check the oxime structure. If I write R here and a hydrogen here, for example, so C double bond N here and R on this side and hydrogen and one lone pair and alcohol on the other side. So if you check this, there is a restricted rotation condition number 1 satisfied. Condition number 2, yes, these two are different and these two are different. So therefore, oxime can show geometrical isomerism, provided these two should be different. Provided these two, the groups added should be different. So from these examples, it is clear that you can also consider lone pair as a group. Okay. So last example, then I'll wind up. Remaining we'll see in the next lecture. That is, for example, if I take cyclohexane 1, 2, or if I take cyclohexane 1, 3, yes. Or if I take cyclohexane 1, 4, yes. These all can show geometrical isomerism because this is the stereocenter here, and this is the stereocenter here, and this is the stereocenter here. These three can also show you. Try to draw the open structure of this skeletal structure with carbons, and then you'll understand. This carbon have two different groups. This carbon have two different groups. Here, this carbon and this carbon have two different groups. This carbon and this carbon have two different groups. So therefore, these three can also show geometrical isomerism. So a quick revision: what are geometrical isomers, and then what are the conditions? Conditions are important. As I told you, first condition is restricted rotation. That restriction can be because of the double bond or triple bond, or can be because of the ring, and different atoms should be bonded. Now, if you take an example of alkyne, If you take an example of alkyne, C triple bond C, first condition is satisfied, no doubt. First condition is satisfied, that is restricted rotation, but it have only one bond. It has only one bond, so no two different groups. No two groups here, right? This carbon have only one bond. This carbon have only one bond. So each carbon should have two bonds. So then only geometrical isomerism is possible. So here geometrical isomerism is not possible. Any kind of alkyne you take, geometrical isomerism is not possible. In the same way, we can also think about N triple bond N. This nitrogen have a lone pair here, this nitrogen have a lone pair. So same logic here. It also cannot show geometrical isomerism. So that's all for today. The topic was how to identify whether a compound can show geometrical isomers or not. Remaining we'll see in the next lecture. Do subscribe, like my channel, and do view my other videos of nomenclature for a clear idea. Thank you very much. Bye bye. Take care.